right, welcome. We're going to be looking at some practice problems with voltaic cells. This is electrochemistry, and we're going to look at how to figure out which elements are being oxidized or reduced in a voltaic cell and how to figure out the reduction potential. Okay, so we're looking at the first two practice problems here. We've got this first one, we've got a voltaic cell set up using aluminum and iron, and you want to figure out who will be oxidized and who will be reduced. And the general rule is the one with the larger reduction potential, so it's got the larger E value, that means this reaction is going to be more favorable. So that is going to be the one that's going to be reduced. And the connection between E and favorability is right here, using this equation right here. So the more positive the E, the more negative the G will be, so the more favorable that reaction is. So the one who is going to be reduced is iron, because it's got the larger reduction potential. Okay, that means that the other substance is going to be oxidized. In order to have a reduction, you have to also have an oxidation, and the one who is worse at being reduced is better at being oxidized. So this one has a lower reduction potential, so it is, worse at being reduced, therefore it is better at being oxidized. All right, so some vocabulary here. We want to label what happens at the anode and the cathode. And remember our trick, an ox and red cat. So the reduction occurs at the cathode, and we know that iron is better at being reduced. So this is the reaction that's occurring at the cathode. At the anode, the oxidation is going to occur, and the oxidation is just the reverse of the reduction there. So I'm going to flip everything around from this reaction right there. Okay, so those are my two reactions. I want to write out the overall reaction. So it's important to know that in an redox reaction, electrons gained equal electrons lost. That kind of goes with the law of conservation of matter. So right now I'm losing 2 electrons, losing 3 electrons here, and I'm gaining 2 electrons over here. So I'm going to think, what's the lowest common multiple of 2 and 3? Well, that's 6. So I'm going to multiply everything in here by 2, and I multiply everything down here by 3. And so that's going to give me 2 solid aluminums and 3 iron ions, and 6 electrons make 2 aluminum ions and 6 electrons and 3 solid iron. And you should notice that your electrons cancel out, so I'm going to go and erase those. Okay. And they should cancel out. If they don't cancel out, then we did something wrong, because electrons gained equal electrons lost. So that is my overall reaction. Pay careful attention to charge. You put the charges in the right place. If you got the charges reversed, it would make it a totally different reaction, so be careful with those. The standard cell potential, the way I like to think of it is thinking it kind of like Hess's law. So the iron, the reduction, which in this case is the iron, the reduction is going to occur as written, so the voltage is negative 0.45. The oxidation, that's going to flip around, and when you flip that reaction around, the sign flips. So now this is plus 1.66. So the standard cell potential, I'm just going to add those numbers up. So it's 1.66 minus 0.45 volts. So that's going to be 1.21 volts. And the delta G is negative NFE. The N represents the number of moles of electrons transferred in this reaction. So there are, in this balanced redox reaction, there are 6 moles of electrons transferred for every what we call 1 mole of reaction. That just means like for every, kind of one of these that happens, we transfer 6 moles of electrons. The F value, you find that on your equation sheet, 96,485 coulombs per every 1 mole of electron. So that just tells you basically the charge of a mole of electron. That's a constant. Looks like our moles of electrons cancel out. And I want to find delta G. So keep in mind, I want to end up with like a energy as my final unit. So I've got, this number is 1.21 volts, But if I write it that way, that doesn't make a whole lot of sense because my unit would be like a volt times a coulomb. So here's where you want to keep in mind. If you look on your equation sheet, it tells you a volt is a joule per coulomb. And again, you don't have to memorize that. It's on your equation sheet. You just have to know to look for it. So a volt is a joule per coulomb. So now that makes more sense as a unit. Now if I multiply this out, I end up with an answer that's in joules per mole reaction. And if you plug that in your calculator, you get around negative 700,040. I want to write this answer with 3 sig figs, which gets tricky with a lot of zeros. So the way I have to write it out is negative 7.00 times 10 to the 5th. If I count my zeros right, 1, 2, 3, 4, 5. Okay. Or the other way I could write it out is negative, and that would be joules. Or I could write it as negative 7.00 times 10 to the 2nd kilojoules per mole reaction. And to find delta K, there's this relationship delta G equals negative RT ln K, and that you can use there.